What exactly is this term drag? Now, this has several names. Sometimes we call it drag, sometimes we call it the drag force, sometimes we call it the viscous force, sometimes we call it air resistance, water resistance, but it all has the same connotation. All of these things means it's a force that simply opposes motion, especially, or rather, opposes motion in a fluid. And when we say a fluid, we mean liquid or gas. And so in the field of kinematics, all right, of course, the most common type of drag force that we are talking about is, of course, air resistance. So if I move in air, okay, with a certain velocity in a certain direction, I always expect to experience a form of drag that is going to be acting opposite to my motion. In fact, we need to understand that the drag force, let's call this Fd, is equal to kv, or sometimes it's equal to kv squared, where k is just some constant. And so the important thing to understand, of course, is that the faster you travel, okay, the larger your v is, the larger the drag is. And that's how drag works. So what is the effect of drag on your motion? So we're going to consider the effects of drag on free fall. And if we think about free fall, well, initially, when you were falling down, there was just this constant acceleration g that was making you getting faster and faster. So if I plotted your velocity with respect to time, right, it would essentially look something like that. Taking up as its positive, which means you could get infinitely fast, which doesn't make sense. So how drag could come and alter this is that, well, since your drag gets larger as your v gets larger, then of course the opposing force gets larger, which means that your acceleration will tend to get a little bit smaller over time. And so what's going to happen if I drew this graph, it'll look something like that. Okay, the slope of this curve is going to get smoother and smoother, and eventually you'll reach a certain situation known as terminal velocity. And that is a situation where, if you look at the forces on your falling object, the weight and the drag, that is where your drag has now equal to the weight, and you have reached a state of equilibrium, and you continue to fall at terminal velocity. Now, we can also look at how drag affects projectile motion. So let's consider an object that moves in this perfect parabola. And if you introduce drag, it's going to oppose both your horizontal and vertical motion. And so the path that you're likely to take now is going to look something like that. And some of the key features that I want to point out is, first of all, look at where your maximum height has shifted. It is now lower for obvious reasons. You oppose the vertical motion, but it's also moving to the left. And that's because the horizontal motion has been opposed as well. In addition, quite clearly, you can see that the horizontal range has reduced, okay, because of the opposing of the horizontal motion. But what is very interesting is that you see the path is no longer symmetrical. It is, in fact, a little bit steeper on the downward path. And that is because by the time you're here, your horizontal velocity has reduced so much that your object just can't really progress very much horizontally anymore. And so the vertical motion becomes a lot more pronounced. And so these are just some of the effects of drag. And we will study a little bit more about drag when we talk about forces.